Okay, so here we go with motion graphs. Motion graphs are another way to describe the motion of objects. And there's three types of motion graphs that we're going to pay attention to. There's position time, velocity time, and acceleration time graphs. And what that means is, for a position time, or sometimes called the displacement time graph, we place our displacement on our y-axis, time over our x-axis, and graph then the change in displacement over time. With our velocity time graphs, or VT graphs, we graph the change in velocity over time, and with acceleration we graph our acceleration over time. What we want to be able to get out of this, our learning targets, is we want to be able to draw position time, velocity time, or acceleration time graphs from a set of data or a given PT, VT, or AT graph. So if I give you a displacement time graph, I'm going to ask you to draw the velocity time graph from that. And then we also want to be able to calculate the magnitude and direction of displacement, velocity, and acceleration from those graphs. Okay? So position time graphs give us three pieces of information about an object's motion. They will give us the displacement, they'll give us the velocity, and they give us the acceleration. So it's a position time graph. Here's an example of one here. This object starts here at the origin at position 0, okay, and its position changes over the first 10 seconds. It goes to position 60 meters. So from this, right, if we take this final position after the first 10 seconds minus that initial position of 0, it gets us our displacement. Okay, so we get our displacement from the final position minus initial position. All right, great. How do we get velocity then from a position time graph? Well, to answer that, let's take a look at what the units are on the axes. It's a position time graph. So on the y, we have meters. And on the x-axis, we have seconds. So if we were to take the slope of a segment on a position time graph, the rise over the run, our units for that slope would be in meters per second. So that's velocity. Okay? So we get velocity from a position time graph by calculating the slope of a segment of that graph. Okay, so let's take a look at the graph we have here. Okay? For this first 10 seconds on here, if we were to calculate that slope, we're going to calculate our final position minus our initial position. So our final position is 60 meters minus our initial position of 0, and it takes place in 10 seconds. That gives us a slope of 6 meters per second. Okay, so that's a positive slope. We have a positive velocity. So if we have positive slope, we get a positive velocity. However, look at the next segment here. In this next bit, between 10 seconds and 15 seconds, there's no change, so there's no slope, so there's no velocity. The object's standing still. From seconds 15 to 40, we have a slope in the negative direction. So our final velocity, our final position there is negative 40 minus our initial position of 60. That gives us a total change in position of 100 meters, and that happens in 25 seconds. So we end up with a velocity, a slope of negative 4 meters per second. So what that's telling us is that if we have a negative slope, we're going to have a negative velocity. So this first 10 seconds, 6 meters per second is the average velocity of this. For the next 5 seconds, it's 0 meters per second because no slope. From seconds 15 to 40, we have a negative 4 meters per second. And then we go back to a positive slope, so we go back to a positive velocity, and that ends up being a positive 2.7 meters per second. Okay? So we want to know, what is this graph showing us? Well, say the object that we're looking at then is this car. This object starts at the origin of 0. At some point then it goes to a positive 60 meters. We'll call that out here. And then it also goes to a negative 40 meters. We'll call that out here. So this object starts here and it moves with a constant velocity of that 6 meters per second for 10 seconds. It gets to position 60. Then it stops there, okay, for 5 seconds, and then it moves in the negative direction. It moves with a negative velocity to the negative 40 meters, and then it immediately returns to the 0 position. So that's the motion of this object. It goes from there, goes here, stops for 5 seconds, comes back to this point, and then back to the 0 point. That's what this graph is showing us. So what about that third bit of information that we can get from a position time graph? What about acceleration? Well, if you look at the slope of these, they're straight sloped lines. So when a position time graph has a straight sloped line, that tells us that it has constant velocity. Therefore, there's no acceleration there. However, if the line on a PT graph is curved at all, say it goes up this way, what that's showing us is that there is an acceleration because the velocity is not changing at a constant rate like a straight sloped line tells us. So let's take a look at this situation here. This graph here, another position time graph, and we've got our position beginning down here at negative 5 meters down here. So here our little dog starts at negative 5 meters, and then it holds still for 5 seconds and then moves with a constant velocity to negative 2 meters. Okay, so then it goes to negative 2 somewhere in here. Okay, and then it holds still for between seconds 11 and 20, and then it begins to move with another positive velocity from the negative 2 meters all the way to a positive 8 meters. Okay, then it holds still again between E and F before moving it with a negative velocity toward 0. So in this case, our object moves with begins without moving at all for 5 seconds, and then moves to negative 2, stops for 9 seconds, and then moves with a constant velocity all the way to negative 8, stops for 10 seconds, and then moves very quickly back to 0. We can tell it's very quickly because this slope right here is quite steep. Here he's moving much slower. Here he's moving somewhere in between that. What is a really good idea for you to do right now is kind of pause and take a moment and try to figure out what the velocities are at these points before then moving on. So here we are with velocity time graphs. So velocity time graphs, we can get the same information from a velocity time graph that we can a position time graph. We can get velocity, we can get displacement, and we can get acceleration. So in this particular graph, we've got the velocity here, we've got our time here. That time is in seconds. And what we see from the graph here, these are straight lines, they're straight horizontal lines. What that's telling us is not that there is no motion. In a position time graph, this kind of line tells us there's 0 motion. Here, this is telling us we have a constant velocity, so we're moving, okay? When our line is here at 0, that's giving us 0 velocity. That's not moving. And here, we're moving with a negative velocity, okay? So to get velocity from a velocity time graph, all we have to do is look to the left. We have to just look to the y-axis at any point in time, and we can find the velocity. So how do we get displacement then from a velocity time graph? So to find displacement from a velocity time graph, what we do is we look at, we call it the area under the graph. Okay, so the area under this portion of the graph in this first 6 seconds is a rectangle. If we were to take length times width of that, right, so that's 1 meter per second times 6, that's going to give us the displacement. So we get displacement from the area under the graph. Okay. What we want to pay attention to is that area is it a positive displacement or is it a negative displacement? In this case, for this graph here, this area is above the x-axis. That's going to give us a positive displacement right there. That's a positive displacement. This area here under the graph then is going to give us a negative displacement. Okay. And another thing to get from a velocity time graph is acceleration. When we look at this line, right, these are straight horizontal lines telling us that this is a constant velocity. So when we have a straight horizontal line on a velocity time graph, that's zero acceleration. Okay. So in this case, in this graph, acceleration is 0. If, on the other hand, our velocity time graph were sloped at all, okay, then we're getting a changing velocity over time, right? So what is the definition of changing velocity over time? That's acceleration. So this, if we're sloped, that is acceleration. Okay. So for this particular graph, what is the motion of that object? You know, with a velocity time graph, we can't really tell if the object starts at the origin or not, right? So we can kind of pick an arbitrary point. And what this object does is it moves with a constant velocity of 1 meter per second for 6 seconds. Then it holds still for another 6 seconds. And then it moves with a negative velocity between seconds 12 and 15. So that motion would look something like this. It would just be moving with a constant velocity for 6 seconds, and then it stops for 6 seconds, and then it moves back with a constant velocity of negative 1 meter per second in that negative direction. Okay, so let's summarize then what we're getting from a velocity time graph. When our velocity time graph is a straight line, we're having constant velocity. So in this case of this graph, no acceleration. We're moving in the positive direction. We know we're moving in the positive direction because our line is above the x-axis. In this case, we're moving in the negative direction because our line is below the x-axis with, again, a constant velocity. Something's moving. Here, we have a straight sloped line, which tells us that we have an acceleration. Because it's a positive slope, we're going to have a positive acceleration. Now, this part, from its beginning to this time right here, it's moving in the negative direction, slowing down. In here, it's speeding up in the positive direction. So with this graph here, what you want to do is you want to imagine your object starting out with some negative velocity, slowing down, and then moving and speeding up in the positive direction. For this final graph on here then, we have an object that starts with a positive velocity, slows to 0, and then increases in the negative direction. The velocity then increases in the negative direction. So this one right here is just like tossing a ball up into the air. The ball would go up and come back down. It would start with some positive velocity, slow to 0 velocity, and then increase speed on the way back down. So let's see what all this would look like then in a case like this here, where we've got this graph here. It's again a velocity time graph, and we've got our dog on a skateboard, and he starts out with 0 velocity and begins to move in the positive direction, increasing his velocity. Okay, so then what happens here at this point? When this is a position time graph, this position meant he stopped moving. This is a velocity time graph. This straight line here means that it is moving with a constant velocity. And then here begins to slow back to zero. So this entire first part right here all takes place in the positive direction. So the way this would look would be our dog down here starts out speeding up and then moves at a constant velocity and then begins to slow to a stop. That happens all within this first 30 seconds. Okay. Then at the 30-second point, that's where he changes direction. So when our velocity graph crosses the x-axis, it's at that point there that the object changes direction. And in this case then our dog would begin to speed up in the negative direction and then slow down in the negative direction. So all of this takes place in the positive direction. It's motion. It's never stopped in the positive direction. Here, at this point right there, he changes direction and then increases speed, then decreases speed to a stop in the negative direction. Now, if you look at the areas of this, clearly this area here is going to be greater than this area here. So our dog doesn't go back to the origin, doesn't go back to where he started. He moves, speeds up, goes at a constant velocity, slows down, changes direction, speeds up, and then slows down to a stop, and never gets back to where he began. So here is a really nice little summary of things. We've got speed, velocity, acceleration, our distance time or position time graphs, straight slope line. This is a high slope, it's fast, steady speed. Here, steady speed, stationary, returning to start. Here, when it's curved, that's giving us acceleration. On a velocity time graph, straight slope line tells us it's uniform acceleration, it's constant acceleration. Here, steady speed, acceleration, and then constant acceleration, back, slowing down. Okay, all of that taking place in the positive direction, never changes direction there. Okay, so take a moment, pause the video at this point to really take a look at the information on this slide. Okay, so here is a really nice little question. I've got a VT graph. We want to know what PT graph matches this VT graph. The best way to handle a question like this on the videos is to pause the video and see if you can figure it out before I reveal the answer. Okay, so what we have here, we have a velocity time graph where we've got a straight line here. That's telling us we have a constant velocity of 4 meters per second. This dashed line simply means that down here we're going to have a negative velocity, negative constant velocity of negative 2 meters per second. Okay, this clearly you're not going to go from 4 meters per second to negative 2 meters per second in an instant. That's why this dotted line here is just ignoring the accelerated motion that naturally would happen here. Okay, so what we want to know is which PT graph down here matches this VT graph here. Well, if we've got a constant velocity here, positive, and a constant negative velocity there, we know that slope on a PT graph gives us velocity. So if a PT graph is a constant, is a horizontal line like this, that means no motion right there. So that eliminates immediately this one and this one. Okay. Only number 2 and number 4 down here show any kind of changing position, show any kind of velocity. So what's happening with this one right here is we've got a constant positive velocity. And it happens to just start at the negative 10 position, move through the origin, and move to the positive 10 position. So it's only positive velocity there, so that's got to be eliminated, leaving us with number 2 only, as the representative PT graph of this VT graph. And if we took the slope of this, it's a positive slope, so we have a positive velocity there. And if we take that slope, that 20 divided by 5, that's 4 meters per second. And this one here will give us, this velocity here will give us negative 2 meters per second there. Okay, so here's another question then. We've got two velocity time graphs. How should their position time graphs be drawn? For this one here, we're starting at 0 velocity, increasing our speed, and then moving at a constant velocity, all in the positive direction. So that position graph, we know that it starts out with some sort of acceleration, so it's speeding up. And then at some point it's moving with a constant velocity, so then it moves with a constant straight line. Over here on this second one, we have a velocity graph that's starting out with some positive velocity, slowing to 0 velocity, then increasing velocity in the negative direction. This, I pointed out earlier, is something like a ball being tossed into the air, which starts out moving in the positive direction, goes through 0, then moves in the negative direction. So the PT graph of this would show us moving up in a positive direction, slowing to a stop, then moving in the negative direction, just like that. So the final type of graph that we are going to look at would be acceleration time graphs. With these, we're graphing acceleration here. So the only kind of acceleration graphs we're going to see will be constant acceleration graphs. So we'll only see acceleration graphs with these horizontal lines on them. Here what this means is we've got an object constantly accelerating at a rate of 5 meters per second squared. Then its acceleration goes to 0, and then its acceleration goes in we have a negative acceleration. So imagine this is like a car starting out from rest. It accelerates at this rate, then that acceleration goes to 0. What this means is that the velocity then would be a constant velocity at that point. And then finally the acceleration goes negative, so our object is slowing down at this point. So this is, imagine you've got a velocity time graph of this. The velocity time graph would show us starting at some velocity, probably a 0 velocity, accelerating at some point, going at a constant velocity, and then slowing. Something like that. Okay? The final thing to understand about acceleration is that speeding up does not always mean positive acceleration. We can have an object that is speeding up with a negative acceleration. Okay? We can also have an object that is slowing down with a positive acceleration. This is how this works. We've got a motion diagram here, and we've got a velocity time graph here. This velocity time graph is showing acceleration, a constant acceleration. The motion graph then is showing us an acceleration in a positive direction. So this is an object that's moving to the right or up and is speeding up. We're going to get a positive acceleration. That's what we'd expect. Here we've got an object moving to the right or up, so it's moving in the positive direction and slowing down. We get a negative acceleration. That's what we would expect. And from our motion diagram we see that the acceleration points in this negative direction right here. Then we've got these two graphs here. These show what you don't really expect. What we have here is we have an object moving to the left, or it's moving down, so it's moving in the negative direction and slowing down. When it's moving in the negative direction, our VT graph is below the x-axis. So we know that that's negative direction. If it's slowing down, it's a positive slope. Okay? So what we end up with is a positive acceleration. If we can see from the motion diagram, our object is moving to the left and slowing down. Our longest arrows are pointing to the right. That is the direction of the acceleration. The right direction is the positive direction, so we have a positive acceleration. Here we have a VT graph that is sloped downward, so we have a negative acceleration in the negative direction, and our object then is speeding up to the left, so we end up with this negative direction. So it's the direction of motion that will help us determine the direction, the sign then of the acceleration. So it's really important to remember. It's the sign of an acceleration, or the sign of a velocity, means direction. We're not ever going to accelerate at less than 0 meters per second squared, but we can accelerate in the negative direction. And so that'll do it for motion graphs.